We are going to start this session with chapter 13, okay? Chapter 13 covers structure, and this is specifically the Lewis structure of the molecule and then the shape of the molecule. So the structure and the shape are related, and in chemistry, the structure that has to do with the type of bonding and the connectivity of the elements in the molecule relates to the shape of the molecule, and the shape of the molecule definitely relates to the function. So ultimately, the shape and the function are related. So if we want to know what a molecule does, we want to see its shape, and then of course see how it behaves and what environment it's found in and all that stuff. And we can relate the shape to the function, okay? So this chapter tells you the bottom line we're going to be covering: drawing Lewis structures, describing the Vesper model, the different geometries, the electron pair geometry when you have 2, 3, 4 regions of electron density around the central atom. So I'm not going to sit here and read all these goals. Please feel free to do that in your own time. What I'm going to do is start working on these goals, okay? Our first goal here is to work on the Lewis structure. So I did try to make a little bit of a list here so I can know what I'm going over. We are drawing the Lewis structure, the Lewis diagram. In drawing the Lewis diagram, there are very specific steps that you want to follow. So I am going to try to follow the steps that they have provided so that I can draw my own Lewis structure. Number one, so here's the information. You will be given a molecular formula that looks like this: CH4, okay, Nh4 plus. The molecular formula has to be given to you. From that molecular formula, you will then start with step number 1, which is you will calculate the total number of valence electrons. And then if you do have charges like we do over here, you will adjust the total valence electrons for the charges on ions, okay? You will then place the least electronegative element or atom in the center of the molecule, draw a tentative diagram, join atoms by single bonds, add in shared electrons to complete the octets of all atoms surrounding except for hydrogen. So once again, you get the idea, right? I'm going through and following the rules. So instead of reading the rules, why not apply the rules? So what I'm going to do here is add a page on the bottom here, and I will apply the rules as I'm going along, okay? So let's see. I'm trying to follow these rules that we have right here. That's okay. I think I remember the rules, okay? So let me start with this. Given this formula, CH4, our goal here is to draw Lewis structure. So I would suggest when you're working on your homework or your lab, you actually follow these steps in drawing your own Lewis structure. The number 1 step said, calculate total valence electrons, okay? So looking at what I have here, I have, in my formula, I have carbon and I have hydrogen. So one thing I realized I don't have here is the periodic table. So you want to go ahead and pull out your periodic table and realize that carbon is in group 4. And because carbon is in group 4, it has 4 total valence electrons. Let me see if I have this right here. I just realized something. I may have a periodic table. Well, I do have this one. Okay. So for the sake of what we need right now, can I annotate here? Will it allow me? Let's see. Draw. This is group. Oh, look at that. Group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8, right there. So the carbon I'm looking at is right here. It's in group 4. So because carbon is in group 4, it has 4 valence electrons. Then we have hydrogen right here in group 1, and that has 1 valence electron. Okay, do I click out of this? It's been a minute, y'all, since I use this. Okay, so now I want to go back to this. Oh, the annotations remain. We'll figure it out, guys. We'll figure it. Oh, is it gone? No, it's still here. Okay, how do I get rid of them? So you saw what I did, right? Let me go ahead and clear these. How do I clear these? Eraser. Sorry, I'm using so many different things right here, so things are overlapping, but let's see, I think I got it, right? Yeah. So back to, yeah, I got it. Back to this. So carbon has got 4 valence electrons, you saw that, and hydrogen has 1. In the formula right here, you see the one that is missing is implied belongs to carbon. So we know we have 1 carbon in the formula. So total valence electrons is 4. We have 4 hydrogen because it's 4 belongs to the hydrogen right here. So times 4, giving us a total of 4. So from the element carbon, we get a total of 4 valence electrons. From the element hydrogen, for each hydrogen, we get 1 valence electrons, but since we have 4, we end up with 4 total valence electrons. So in the compound, in the molecule, we end up with 8 valence electrons, okay? So I'm gonna kind of digress and go my own path, but I'm still trying to follow a set of rules. The next thing you do is select central atom, okay? The central atom has very specific characteristics. One way to tell what a central atom is you have fewer number of atoms. Sometimes you have 1 of a central atom. If you have a much bigger molecule, you may have 2 or 3, okay? Fewer number of atoms in formula. Most likely that atom is your central atom. In our case, carbon would be central because we only have 1 carbon when we have 4 hydrogen, okay? Next one, hydrogen is never central atom, okay? At y'all's level, hydrogen is never central atom, okay? Hydrogen is never a central atom. It doesn't have enough bonding capacity to be able to host other elements around it, okay? C, when you have competing central atoms, the central atom usually has a lower electronegative value, okay? What does this mean? i.e., let me just say i.e., further, how do you spell further? Further, no, I think it's the other one, further away from fluorine. Yeah. So whatever element is further away from fluorine tends to be the least electronegative, except for hydrogen. Remember, hydrogen can never be central atom. So you want the element that's further away from fluorine, okay? So these are the characteristics of the central atom. So looking at what we're working on here, okay, fewer number of atoms in the formula, hydrogen is never a central atom. And then, yeah, okay. So in my case here, in our case, carbon is central atom, okay? So for that reason, let me see. Carbon will be in the middle, and then you want to draw the 4 hydrogens around it. The hydrogen above, below, to the left, and to the right, okay? I need to add some more pages. How do I minimize that? This looks very different. Oh, add a page there. So the page has been added. Let me go ahead and exit out of here. We are on rule number 2. Now we're moving to rule number 3. In rule number 3, we have figured out our central atom. Now you use 2 electrons from total valence electrons to form single bond between central atom and surrounding atoms. The surrounding atoms are also called peripheral atoms, okay? So I need to kind of go back, but I won't go back. I'll just redraw my structure right here. And then I'm going to add my total valence electrons on the side. So my total valence electrons were 8 electrons, right? 4 from carbon and 4 from hydrogen. So it says here, use two electrons. Remember, one bond is made up of 2 electrons. So each time I draw a single bond or a single line, I'm having to use up 2 electrons from the total, which is 8 electrons. So I'm going to draw a bond here, another bond here, another bond here, and another bond here. I have drawn 4 bonds. These 4 bonds uses up a total of 8 electrons. So from the bonds, I use up 8 electrons and I'm left with 0 electrons. It's important when you're drawing the lowest structure to end up using all the electrons you had available in your total valence electrons before you start doing any double bonding, okay? So looking at this right here, I'm out of electrons. I'll check with number 4, which is check to ensure central atom has octet of electrons. And by the way, if you're watching this video from yesterday, you're realizing I'm using a slightly different step, right? Just so you know, this more organized step-by-step process allows you to draw more Lewis structures versus the one I showed you yesterday. The one I showed you yesterday is more like a quick way to get the Lewis structure if you're running out of time. This one is more detailed, it's equipping you more to draw more Lewis structures, okay? So check to ensure central atom has octet of electrons. Carbon does have 8, right? 2 from here, 2 from here, 2 from here, and 2 from here. Carbon is surrounded by 8 electrons. Well, what's the story with hydrogen? Hydrogen has 2 electrons. So remember we mentioned this yesterday. Hydrogen follows the duet rule. It's not a singing group, shoe up, shoe up. No, this is a duet rule saying at best it can have 2 electrons. Duet stands for 2. But then carbon follows the octet rule. So at best, carbon has to have 8 electrons. And it does. So this is a valid Lewis structure. Okay. Now there is more to this than that, but what I'm going to do is as I'm working on the different structures here, I'm going to unfold the additional information. So let me see. Add page. No, right here. Add page. Add page. Okay. So what I'm going to do here is I'm going to follow the rules that I just showed you guys right now to join the lowest structure. The next one I'm going to be drawing is Nh4 Plus. So this time I'm not writing the rules. I'm just going to be following the rules. And then when we get to the part that's different, I will show you the part that's different. Okay. Next one is Nh4 Plus. Once again, we're going to be drawing the Lewis structure for Nh4 Plus. Lewis structure. First thing, nitrogen and hydrogen. These are the elements we have in our formula. Now, this formula happens to be not a compound, but an ion, right? Specifically a cation because it is positively charged. Oh my goodness, this word reminds me of this situation, right? I was trying to illustrate a lesson to my husband who's sitting right there, okay? And I'm telling him, I was telling him to read something, and then he read it as this word here as cation. And I said, cation? He said, no, it's called cation. He said, what? Nuh-uh. What do you mean cation? That's cation, like vacation. Nobody says cation. I was like, oh my goodness. I know. I said, I can't believe I married you. I'm just kidding, y'all. This conversation never came up when we're dating. Okay. And in our formula, we have 1 nitrogen. So nitrogen is in group 5, and we have 1. This is going to be 5 right here. Hydrogen is in group 1 as before, but we have 4 in the formula, right? So we have 5 plus 4. We said yesterday, in order for a formula to obey Lewis structure, to obey octet rule, not Lewis structure, the octet rule, it has to have an even number of electrons. If we continue this path, we may end up with an odd number. But what do we do with this positive right here? To adjust for the charge, because we have a positive, in chemistry, positive charge usually means you have lost an electron. So here it just means lost 1 electron. The symbol here stands for electrons. So our total valence electrons is technically really 9, but minus the 1 electron that got lost, now we're left with 8. Okay, just like before. I'm going to select my central element, which would be N, not H, never H. surrounded by my 4 H's right here, H, 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 and H below, okay? And then I have to draw single bonds with my 8 electron. Remember, each single bond uses up 2 electrons here, 2 electrons here, 2 here, 2 here, and we end up with 8 electrons. So even though I had 8 electrons here, I've used all 8 in drawing my single bonds, just like before. Check with nitrogen. Is it surrounded by 8 electrons? Yes, nitrogen has achieved octetness, just octet. And then what about hydrogen? Has it achieved duet? Yes, it has, because hydrogen is surrounded by 2 electrons in that bond, okay? Hydrogen has access to the 2 electrons. Nitrogen has access to all 8 electrons in the bond surrounding nitrogen, the ones touching nitrogen, not anything beyond that, okay? So this would be your Lewis structure. Now, mind you, I have all these electrons here for illustration, but on your structure, you'll be missing all these electrons. This is just to show you what's going on, okay? Now, I want to add over here, because we have an ion, a cation, general chemist or inorganic chemist. This is a specialty in chemistry. They like to draw brackets around the formula and put a positive charge to say that the number of electrons were adjusted by 1 because 1 electron got lost. And this, the original formula here, is actually a cation, okay? Now that we're done with this, we're moving on to one that's an anion. For that, I'm going to be using CO3, 2 minus, okay? In this case here, once again, I'm going to start with, let's see, total valence electrons. Total valence electrons here, I have carbon, I have oxygen. In my formula, I have 1 carbon. And in my formula, I have, oh, I did the opposite way, my bad. I was like, well, how did I do it again? Carbon is made up of, is in group 4. So it has 4 valence electrons, right? And oxygen is in group 6. So it has 6 valence electrons. Carbon, in this formula, we only have 1. You can see that here. We have 1 carbon, so this is 4. Oxygen in this formula, we have what, 3? This is going to be 18, correct? Now, in this formula here, we have a 2 minus. How do we treat this 2 minus? In chemistry, 2 minus just means you have an extra 2 electrons. So adjust for charge, you add 2 electrons. And so we end up with what? 24 electrons, right? 4 plus 18 plus 2 is 24, okay? Let me drink this. Somehow it feels a little warm in here. Okay, so we have 1 carbon and 3 oxygens. For that reason, the 1 carbon has to be a central atom, and they're surrounded by 3 oxygens right here like this, okay? Now we're going into a territory that kind of pushes towards general chemistry. I will try not to get into general chemistry, but just kind of, explain why I am adjusting for certain things. But anyway, so from here, remember, I have to draw single bonds between the central atom and peripheral or surrounding atom. A single bond here, a single bond here, a single bond here. So 3 single bonds each uses up 2 electrons. So I have used up a total of what? 6 electrons. And I'm left with, normally I'll rely on you guys for that head math stuff, because when I'm doing all this chemistry, my brain is like, overload. I'm not doing head math. I'm using my calculator, you all. I'm using my calculator. Yeah, you heard me. And I'm left with 18 electrons, okay? With 18 electrons, you're then going to do something that we haven't done before, which is if you have extra electrons left over, this was in the rule, add 6 electrons to the surrounding atoms to make octet. I should say to achieve. Let me go back. I can do better. To achieve. You're trying to achieve that status, right? Surrounding atoms to achieve octet, right? The surrounding atoms want to achieve octet. So you help the surrounding first. And I'm going to do that right now. and you add 6 electrons. And the way you're adding them is a pair at a time. So you're adding 6 electrons, a pair at a time. So I'm going to add them in pairs, right? 1, 2, 3, 4, 5, 6. And since I do this a lot, I kind of have this rhythm, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. I did this 3 times. 3 times 6 is 18. So I essentially use all the remaining 18 electrons to help the outer elements of the surrounding atoms achieve octet. How do I know we have achieved octet? Each oxygen has this combination or configuration of electrons. You got 1, 2, 3, 4, 5, 6. And then in the bond, you have 2 electrons, so 7, 8. That oxygen is surrounded by 8 electrons. Is how it's seen, okay? Okay, so everything should be good, right? The surrounding atoms are at 8 electrons, 8 electrons, 8 electrons. But what about the carbon? I mentioned this yesterday, that when you have carbon, nitrogen, oxygen, and fluorine, these tend to achieve octet. They have a goal, but they usually meet that goal. Carbon doesn't have octet. How do I know? There's only 3 bonds around the carbon. Carbon at best is at sextet, but it wants to get to octet, 8 electrons. So here is where you can pick any of these carbons to help, any of these oxygens to help the carbon get to octet. I'll pick that one, the one on the right. Why? Just because. So this one, this carbon here will actually double bond with the central carbons. Because remember, we're out of electrons, right? So here, this is a very important point I need to make right here. Let me go back. Remember the electrons we had here? You can't just add 2 electrons, 2 dots here and say, well, now carbon has an octet because we are out of electrons. Remember, we are out, 0 electrons. All those dots and lines came from here. But what we can do is ask any one of the surrounding elements to help carbon out to get to, I erased everything, to get to 8 electrons. So I removed the electron dots from there and converted the pair of electrons from a lone pair electron to a double bond or to a second bond, right? So I have to introduce an additional rule. And the rule here is if you ran out, I can't spell, out of electrons, comma, and the central atom has not achieved octet. Okay, so we have a situation, right? Central atom hasn't achieved octet, but you are out of electrons. What do? Use a pair of electrons to form multiple bonds. A pair of electrons from surrounding atoms to form multiple bonds until octet is achieved, okay? Remember, every other element, all the surrounding elements already have octet. You're not trying to have the central one achieve octet. And so the surrounding ones are helping the central one achieve octet. So you use a pair of electrons each time, a lone pair of electrons, okay? So when I say a pair here, I mean a lone pair of electrons to help the central one. That's what I did right here, okay? And then you want to check. I had to do it only once because by this point here, now the carbon has 8 electrons. And this is essentially the long way of doing the lowest structure, okay? I'm going to show you one more picture, then I'm going to come back to this structure right here, and we're going to talk about resonance structure. I was going to do it with NO3. I think I'll do it with NO3 just to give you guys a little bit more experience. Okay, I'm going to do one more here with my lowest structure and work on NH. Actually, no, let me not do NH3. Let me do PH3, okay? In pH3, P is phosphorus. Phosphorus is in group 5, and I have 1 in my formula. Hydrogen is in group 1, and I have 3. So 5 times 1 is 5. 1 times 3 is 3. When you add this, you get 8. Okay? My formula has a total of 8 electrons, total valence electrons. Okay, phosphorus ends up in the middle, surrounded by 3 hydrogens, right? And then I have to draw my single bonds first. That's the rule. Single bond, single bond, single bond. Each single bond uses up 2 electrons. So I've used a total of 6 electrons out of my available 8 electrons. I am left with 2 electrons. Now, you probably want to add electrons to the hydrogen. Don't. Hydrogen cannot accept additional electrons. So hydrogen follows the duet rule, which means it doesn't need, I can't spell. Hold on a second. Need additional electrons. So guess where these electrons go? They go on the central atom. So what are you going to do here then? Place extra electrons on the central atom to help it achieve octet. And sometimes you find yourself having more than the central atom needs to achieve octet. Just go ahead and dump any of the extra electrons that were not used, okay? So any extra electrons you have, you want to place those on the central atom to help it achieve octet. So we had 2 electrons that were not used, place them here, and that's essentially it. -2, we have 0 here. So I'm gonna go ahead and let's see, what do we have? Each hydrogen has 2 electrons, and the phosphorus here has what? 8 electrons, okay? Give me just a moment right here. Okay, let's see. Our next molecule will actually be one that we have worked on. Well, actually, I'll do a different one, so it should be fine. Let's see. Wait, hold on just a second. Okay. Okay, so we're going to pick up where we left off, and this time we're going to be working on Nh4. This is the last formula I'm going to be working on. With nitrate, Nh4, we're going to be working on the lowest structures, and this is nitrate ion. It's an anion versus a cation. I'm going to use this to show resonance. So our goal here is to draw a Lewis structure, and then we're going to be talking about resonance structure. So resonance structures exist, resonance. Resonance structures is essentially the extension of a Lewis structure. So once you draw the Lewis structure, and I usually explain this in class when we're face-to-face, say, for example, you follow the rules and you end up with one structure, and I follow the rules and I end up with a different structure, and both structures are valid. Who is more correct? There are 2 things that we look at. Well, I should say, yeah, 2 things, 2 products that come out from the Lewis structure that we look at, okay? Which is essentially, one of them is resonance structure. In the resonance structure, you have 2 Lewis structures that are essentially alike, and the only difference is where the double bond is placed, where the multiple bond is placed. So where the electrons are placed, that's the only part that's different. So here, essentially in resonance structures, what we see is atoms are in the same position in 2 or more different structures. See, if the atoms in the same positions, what is different? The electrons. And what part of the electrons is different? Double bonds. double bonds are in different positions, okay? So that's the issue here. And that's how we generate or create what we call resonance structures. So one structure is a resonance structure of the other if they look almost identical, but the only thing that's different is the placement of the double bonds. In that case, a double bond will be switched out with a single bond, okay? The other thing we see in Lewis structures is something called, let's see. And by the way, all this I'm explaining is kind of premature because we actually see what I'm talking about down here. We're talking about resonance structures, and then of course, ultimately isomers. So I'm gonna kind of talk about resonance structures, and then we talk about isomers. Okay, so from the Lewis structure, you can get a resonance structure, you can get an isomer. How is an isomer different from a resonance structure? In the isomer, the atoms are actually in different positions. Atoms are in different positions. So here, the differences in the two valid Lewis structures are not as subtle. They're more obvious, okay? In two or more valid Lewis structures. So I'm gonna start here by showing you an example of resonance structures first, okay? In this ion here, nitrate. And then I'm going to use a different formula, HCN, to illustrate the existence of isomers. Once again, both Lewis structures are valid, but in the case of isomers, the differences aren't as subtle as they are in the resonance structures. The differences are more noticeable, okay? So starting with nitrate, let me start with nitrate. And once again, our goal here is to illustrate resonance structures. So I'm going to start with nitrogen being in group 5, and we have 1. Oxygen is in group 6, and we have 3. And then we have the extra charge. And the extra charge here is going to be just, because we have 1, you add 1, right? So we got 5 here, here we got 18, and you add 1, and we end up with what, 24? Let me make sure, let me verify this math, because I cannot trust just looking at this and trying to make sure. I just prefer verifying it, okay? I'm talking a lot. Okay, 24 electrons. Since I know how this is going to end up, I am going to start off by drawing my Lewis structure in the middle. I'm going to draw this Lewis structure right here. Nitrogen in the middle surrounded by 3 oxygens. I have 24 electrons to deal with, right? So I draw a single bond here. Here, 2 times 3 minus 6, we're left with 24 minus 6. I know, 18 electrons. 1, 2, 3, 4, 5, 6. 1, 2. I didn't follow the order. Oh my goodness. Okay, sorry. Let me go back. I can do better. Hold on. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm trying to follow the order. It's so hard because I'm trying to get to the point I'm trying to make. So by using 6 dots 3 times, I pretty much just use all 18 electrons. Okay, I'm out of electrons. So here's where the situation happens. Each oxygen has 8 electrons, right? This is where I was rushing to get to. Each oxygen has 8 electrons, but the nitrogen only has 6 electrons. Nitrogen has to have 8 electrons. So nitrogen is going to need help from any one of those 3 oxygens. So what I'm going to do here is, actually, you know what, if I can, let me go ahead and copy this. And make this slightly smaller. And then copy and paste. Okay. Hold on. What did I do? Okay, let me erase this first. Copy this. Copy and paste right here. Then I'm going to paste it again right here. Do I have enough room for all 3? Okay, there. So now I have 3 scenarios here, right? So in the middle nitrate, I am going to take the electron pair from up here. Oops, I think my circle is a little too big to form a double bond, okay? And remember, this here is an ion. So let me go ahead and remove the charges here. I don't need those anymore. Let me bring back the dot. This is going to be negative. Then same thing happens here. Remove these. Oh, probably should have done that before I copied them over. You know, hindsight is 20/20. That's me. I'm always wondering if I could have done a better job of what I'm doing there. Because these are all negative ions. Excuse my pictures, they're not perfect. But you see, you're going to be using this double-headed arrow to indicate resonance structures. Okay, the double bond in my central nitrate ion is vertical. The one on the right will be on the right side, and I'm going to have to remove the lone pair from here. Oops. The circle I have here with the eraser is very big, so every time I touch something, it just erases a lot in that area. Okay, right here, let me see. The one that's missing is on this side. I need the eraser function. Can I get in here? Nope, you can see it's very big, right? It's okay, I can always redraw this. Okay, as you can see, the double bonds seem to be rotating around between each N and O, right? These are three valid Lewis structures, but they're not the same Lewis structure. Essentially, in the world of chemistry, the position of the double bond does matter spatially. The first one here, number 1, has a double bond on the left. So just to kind of illustrate this, we can say that we have 3 different oxygens, right? Let's say oxygen 1, and you got 2 here, and you got 3. If you were describing this to someone, you would say the double bond is between nitrogen and oxygen 1. Keeping the same convention, 1, 2, 3. In the middle one, in the middle resonance structure, the double bond is between nitrogen and oxygen 2. See? And then in this third resonance structure, you got 1, you got 2, you got 3. The double bond is between the central nitrogen and oxygen 3. So these make the 3 equivalent, very similar resonance structures, okay? Well, if that's the case, then who won? If this was a competition, who won? What is the actual structure of nitrate ion? The actual structure of nitrate ion is as follows. It's actually what we call the resonance hybrid. Okay, you know how you have a hybrid car, and the hybrid car essentially marries 2 technology. You have the electrical part of the car, and you have the combustion chamber or the gasoline part of the car, right? And both, they coexist together. So you have a hybrid, 2 systems coexisting together. Here we have a hybrid of the structure, and the hybrid isn't just 2 of these kind of merged together. You actually have all 3 structures merged together. How do you draw that? You draw the nitrogen in the middle, surrounded by the 3 oxygens, top, to the right, to the left. And then in the resonance structure, you can see the only thing that really changed here was the double bond, right? Oh, I like the yellow color better. The second bond, that was the only thing that changed here. So in the hybrid, that would be the only part that changes. The single bonds are exactly where they are, but everywhere you have the double bond, you want to redraw the double bond. Only you don't have enough electrons to distribute and have full double bond. So what you do in this case is you draw dotted lines like that, like this, and like this. And sometimes you're asked to figure out what the bond order is, the value of the bond. And essentially you have a second bond, a double bond, divided in 3 equal elements, right? It's divided here, here, and here. So the value of this bond here, called the bond order, is equal to 1 whole bond and a third, sometimes written as 1.33, okay? Just to show you that the second bond is equally distributed between 3 possible locations. And so that's the value of that bond. And then when you're showing this here, you don't show the lone pair electrons. You just draw this like that, and that suffices. And this is called the resonance hybrid, where it shows you all 3 resonance structures combined together to form this hybrid. okay? Okay, enough with the resonance structures. Now we're moving on. So remember, the real nitrate ion exists like that, but right before it bonds, the electrons can take the position of either 1, 2, or 3, and then the bonding takes place. So I wouldn't say it's deceptive of the molecule, but molecules have certain comforts they have when they're by themselves, or ions have certain comforts they have when they're by themselves. And then when they're about to form a bond with another ion or element, then they change to adapt to make that bond possible. It's kind of like shaping up right before you get married, you know? It's not deception. It's just trying to make the bond work, right? The bond possible. Talking about this. Anyway, now we're talking about, what was the other thing we're talking about? Isomers. Okay. Isomers. In the case of isomers, I'm going to show you HCN, right? The assumption is C will be in the center because of how I wrote the formula, but that's not necessarily the case. There are two ways you can draw this, right? Let me get the number of valence electrons. Hydrogen, we have 1. In the formula, we have 1. Carbon, we have 4 valence electrons, right? And 1 atom in the formula. This is 1, this is 4. Nitrogen, we have 5 valence electrons, and we only have 1 in the formula, so we now have 5. When you add all this, you end up with what? 10, okay? So, of course, based on the rules, hydrogen is not in the middle. Between carbon and nitrogen, remember the periodic table has carbon, nitrogen, oxygen, and fluorine arranged this way. You can see carbon is the furthest away from fluorine, so carbon would have to be in the middle. But I propose there is a valid Lewis structure in which nitrogen is in the middle. So not to confuse you, I'm just saying that there is more than one way to draw a Lewis structure where it works out. But in general chemistry, we use certain rules called formal charge that actually ends up telling you that this is the much better structure, okay? So we got C here, we got N, we got H. I got N, I got C, I got H, okay? I'm gonna follow the rules. 10 electrons to work with. So I put a single bond here, single bond here, single bond here, single bond here. These are two separate structures. So I'm using 4 here, right? -4. And over here, same thing, same scenario. Let me draw its own set of electrons so I'm not confusing to people. Same thing. This is for this on the right, okay? So I'm using 4 electrons. I'm left with what? I'm left with 6. The 6 electrons here go here, 1, 2, 3, 4, 5, 6. They cannot go on hydrogen because hydrogen cannot handle any more electrons, okay? Here I'm left with 6. These 6 go on nitrogen because the hydrogen cannot handle any more electrons. -6, I end up with 0. -6, I end up with 0. So I'm out of electrons in my electron bank, okay? To the molecule on the left, let's see. Nitrogen currently has 8 electrons, right? 6 via dots and 2 via single bonds. Carbon currently has 4 electrons, so it's not an octet. Nitrogen is an octet. Hydrogen is satisfied with 2 electrons. Okay, do it. Okay, over here on the right, I got 8 electrons again for carbon. Carbon is good. Nitrogen only has, 2 bonds, so 4 electrons, right? Hydrogen has 2 electrons. So nitrogen is missing 4 electrons on the right. On the left, carbon is missing 4 electrons. So let's help on the left, carbon to get to octet. On the right, nitrogen to get to octet. So over here, I'm going to erase. Okay, I need to minimize the size of this. It's making it a little bit difficult. Yeah, that should work, right? Let's see. Okay, let's go back here. Oh, so much better. Okay. Actually, let me go ahead and erase the top one. Okay. If I erase the top one, I make a double bond here from the lone pair that I erased. Then let me go ahead and erase the bottom one. And then use that to make a triple bond because the first only allowed me to get to 60 electrons. Now let me check real quick. What do I have? Around nitrogen, I still have 8, right? 1, 2, 3, 4, 5, 6, 7, 8. On carbon, now I have 4 bonds. 4 bonds equal 8 electrons. So now I have 8 electrons. So it looks like my Lewis structure on the left is good. On the right, let me see. I'm trying to help the nitrogen get to 8, right? So I need to add bonds. So I'm going to go ahead and do the same thing over here. Remove that lone pair, make a bond out of it. Nitrogen is now not at 4 anymore, so 6 electrons. Do it again. Take this, erase that, and we're now at 8 electrons. And so this looks good, right? So technically, these are 2 valid Lewis structures. But like I said, in general chemistry, the majors level class, we learned that ultimately this is a much better Lewis structure because it has something called a lower formal charge. We are not learning formal charge in this class, so the rules that we have ultimately tell us the left Lewis structure is the better one. But this is just showing you isomers. In the isomers, you have more than one valid Lewis structure, but they look very different, okay? Moving on. Oh, I've already done this, so I can check this off. Done, check. With this one here, I'm going to just do a shortcut, right? So we're drawing, the typo here, HCO3 minus, okay? So it shows you here, hydrogen contributes 1 electron. We only have 1. We have 4 carbons. Sorry, we have 1 carbon. Each carbon contributes 4 electrons. We have 3 oxygen. Each oxygen contributes 6 electrons. And then you have the extra charge from here. So when you add everything up, you have 24 electrons. So remember, right? Now, when they did this part here, I want to take a step back and kind of show you how they did this part real quick. I'm not going to go into all the details, but remember you have HCO3 minus, and we have 24 electrons to work with. Hydrogen can never be in the middle. So in this case, carbon is going to be the central atom because remember, in the SNOF, carbon is furthest away from fluorine, right? So carbon will be in the middle, central atom. You have hydrogen, you have oxygen, and then, well, you could try to have oxygen down here. Here's the issue though. Because of the number of electrons we have, this structure will not work if you put the oxygen down here. And that's why they have the oxygen as an additional central atom over here. So I just want to mention this to you. Don't worry, this is a little tricky. So for this part, it's more just letting you know that there are other combinations out there. You will not be required to reproduce this on the exam. Don't worry about it. Not for this class, okay? So now that we have here, this is our first central atom. Now the oxygen is forced to be in here as a second central atom, with this being a surrounding atom, this being surrounding, this being surrounding, okay? In a way, it looks like surrounding, okay? We have 24 electrons to distribute, so form a single bond between all the available elements. 1, 2, 3, 4. 4 times 2 is 8. 24 minus 8. Oh, why does my calculator keep falling asleep? Wake up, calculator. 24 minus 8, 16, okay? So we got 16. So what we're gonna do here is, let me take this out from here. I need a space right there. I'm gonna place, I have 16 electrons left. I'm gonna place 6 electrons around the surrounding elements into the surrounding right here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And this is minus 12, right? 6 times 2 is 12. We're left with how many electrons? 4. And the remaining 4 electrons will normally go to the central atom. But in this case, let's see, we have 2 sets of central atom. Am I doing this correctly? Because they say we have 24 here, right? Okay, so I put 6 here, I put 6 here, and I put, okay, that's okay. I'll put 1, 2, 3, 4, okay? So I'm gonna help this oxygen first, just because, so you're probably wondering, why did you help the oxygen first, not the carbon? I'll tell you in a little bit. The oxygen is surrounded by hydrogen. Hydrogen doesn't have any lone pair electrons. So if the oxygen is found to have less than octet, the hydrogen can't help it. And if you look to the right, carbon doesn't have any lone pair electrons either. So carbon can't help oxygen. So we really need to give oxygen the lone pairs, right? It does get complicated sometimes. Now, On the other hand, if you look at this here real quick, hydrogen has 2 electrons. This oxygen has got 8 electrons. This one here has 8 electrons. This has 8 electrons. This carbon has 6 electrons. It's needing 2 to get to the octet. Can it get help? Yeah. From where? From many places. It can get help from here, and if necessary, from here. But there are priorities. So the first 2 priorities are these oxygens. Yeah, now it gets a little bit complicated here. Okay. These oxygens will give up their lone pairs first before that oxygen. You're probably wondering, well, how am I supposed to remember all of this? I'll show you something in a little bit. Let me tell you right now. In general, carbons tend to prefer having 4 bonds. It can be that combination. It can be this combination right here. It can be 3 on one side and a single bond. But carbons prefer, oh yeah, like that. Carbons prefer, I forgot one more combination. Single bond, double bond. Yeah. Carbons prefer to be surrounded by 4 bonds. And you have these 4 possible combinations right here. Okay. The carbon will take one of these combinations. When it comes to oxygen, oxygen prefers to have this combination here or that combination right there of bonds. Okay, so either this or this. And as you're drawing a bunch of different Lewis structures, you start to see deja vu, right? Patterns over and over again, where oxygen prefers either this combination or this combination, having 2 bonds and 2 lone pairs, while carbon prefers having 4 bonds in these 4 possible combinations. Okay, so, and then of course, hydrogen prefers this. Simple, straightforward. You see that all the time. Okay, so back here, only one of these oxygens can accomplish that. And that will be either the top one, making the double bond, right? And then this one here will not be able to accomplish it. Now they're showing this to you, where was I? Yeah, over here, right? Using the resonance structure, that if the double bond is not between this carbon and this oxygen, you have one resonance structure. And of course, the other one will be similar to this, where the double bond is in between the carbon and the lower oxygen right here. So hopefully you're seeing, what did I do? Oh, snap. Oh, my bad. Hopefully you're seeing the trend right here, right? Yeah, hopefully you're seeing that. Okay. I've talked about this, this, and this. And now I'm ready to talk about valence shell repulsion theory. Oops, sorry.